This is an interactive presentation. It contains a lot of WebGL demos in your web browser, so you can do the QR code thing and follow along and be amazed that it works on my phone or on my laptop. So let's go. This goes back to a year when I was working a lot with Leaflet, and the main problem that Leaflet had is people complaining, if I load 5,000 points, it goes slow. And the answer is yes. It's a browser, it's not designed to have 5,000 images in the web page, of course it goes slow. Fast forward a couple of years, Mapbox starts to take the highlights because it works with WebGL, it works way better. I have done all the Leaflet plugins I could do and squeeze all the functionality of HTML I could, and we still had the same problems. People complaining, if you load 5,000 points in Leaflet, it goes slow. So then Leaflet kind of decayed a bit. And I got angry or annoyed with the other WebGL libraries because I don't really understand the architecture or I have disagreements on the technical parts. So I started to write my own from scratch, starting from a WebGL abstraction library, which is the foundation for the whole thing. In a very object-oriented manner, because it's the only thing that my brain can really understand, object orientation. A year later, after I had the WebGL foundations, I started on the geometric foundations. The antimeridian, the poles, projection data, projection and reprojection code, all these kinds of boring, very difficult things that have to be done the right way for a library to work. So a year later, I started putting things on my map, like circles and lines and polygons, because after 2 years I had foundation. Third year I could actually start putting actual data on it, like map tiles and little pins. And congratulations, you just spent 3 years to make this. Bravo, tap on the back. This year, however, I have been having some fun. I have been squeezing object inheritance in my library. I have been doing animations. I have been doing lines, because lines in WebGL are difficult. And scalar fields, which is going to be fun to see. So the first thing I'm showing here is the tinted sprite. The pin on the left is a normal classic Leaflet pin. It's a PNG image in your browser. The other three, however, are the same image. It's a white image, and I'm tinting it on the GPU. So it's useful, and it shows that you can do things in the GPU with actual sense. How you use it in JavaScript is like this. And this, if you have worked with Leaflet, this will feel familiar for JavaScript. You just instantiate the object as a tint, color, as a CSS color string, or an array of numbers, or a hex color, or whatever you want, and then you multi-add the sprites. This is the trick that makes my WebGL implementation go fast. One of the main bottlenecks in WebGL is communicating with the GPU. If you add 5,000 points one by one, that means 5,000 communication with the GPU. If you do a multi-add, my library will squash all those points together and do one communication with the GPU to upload the data. Internally, how this works is it has the WebGL shader, and the difference between the normal sprite on the top and the tinted at the bottom is that I multiply the color by the tint color. And the rest of the implementation of this tinted sprite is 100 lines of code to make sure that this value has a value. And it's nice. The way it works is I build classes on top of classes. So I have the Platina, which squashes everything together, the asset which holds symbol and runs the rendering loop for one given shader, then vertices, which means your symbol is triangles, and interactive, which means your symbol will be able to receive mouse events, and extruded point, which means your symbol is a point geometry, and then all vertices explode, are extruded from there. Then sprite, which means you have 4 vertices exactly, and there's a texture, and there's an image in that texture, and then I tint it. So I can build functionality on top of functionality by means of object orientation. This is another example of a symbol I have been making this year. It's a Monte Carlo fill. Instead of filling a polygon with a full color, I can just drop random points on it, and it works. So you can just zoom on a thing, and you will see there are individual points instead of a full fill. This actually was up there by Jerome. So I have to make this to prove him wrong, or to try to prove him wrong. How it works, that example uses GeoJSON actually, and the way GeoJSON works in my library is very similar to Leaflet as well. You create instances of the GeoJSON with a string for the URL, you don't have to pass it the whole object. then it has a polygon symbolizer which receives the feature, the geometry, and you have to return what symbol do you instantiate for that GeoJSON feature. And that's it. You like toolmap, it works. It's easy to, I find it very easy to work with because I made the API look like Leaflet, which is what I used. So animations, radar strip. This is not really interesting, but it was a proof of concept for animations and how to make sure that the rendering loop does run on every frame. So, you know, it's a radar strip. It's code. It's easy. You can see that no problem. I also made Delunay meshes. This is actually 5 points, with each of them with a color, and the library will call Delunator by Volodymyr, and build all the triangles, and then the color interpolates, etc., etc. So I have 5 points, 5 colors. It draws the triangles automatically to make the minimal triangles, because I guess you know how Delunay works. And
explain.
In 15, I cannot explain it. It's a complex algorithm. It is. Okay. A bit of computer science theory. What I do is usually class inheritance. You take a class, which is a piece of functionality which you can make little objects, and then I add more things on top of that class. That's class inheritance. You take the parent class and then you make a subclass and start making more and more things. There's also something called decoration, which is a design pattern for object orientation. When you decorate a class, you're putting stuff on top of that class, but you can modify which class you're decorating. Okay? We'll see this like this. How I'm doing the tinted sprite is I'm taking the sprite, and internally my library will do class tinted sprite extends sprite. So I will be making something that builds on top of sprite. For decoration, I can have an existing class like a circle. I can have a decorator like Bouncify, and I create a new class, bouncing circle, by decorating the class. And then I create my bouncy ball symbol. So the first one I did is the intervalify. This is sprites. This is 40,000 sprites, and they all have a number for the interval they belong to. And I can change the interval I can view on my map, which is nice. And this works for time intervals or m-value intervals or whatever. And you can apply this decorator to any symbol, not just sprites. So that's why you have to choose what are you going to decorate. They work like this. Decorate the class on all the sprites, and then you need a reference to the asset name that this is what rendering to. So this is going to be common for all the symbols. And these numbers will go into the GPU, and the GPU will filter all the symbols that are outside of the interval, and it magically works. Differ. Differ is an old technique for making something semi-transparent by randomly or pseudo-randomly taking pixels out. So all of these things, the polygons and circles and the sprites, they have different values for the differ. So a random amount of their pixels is going to be transparent. This shows that I can apply a decorator to different base classes or different symbols, like that. I can apply this decorator to different symbols to get different decorated symbols. And a Bouncify. Don't laugh, because this was a business requirement for me.
What?
An actual business requirement. They paid me money to make things bounce, okay? And it's nice. That's it. It works on your phone. You don't have to take a photograph. You have the slides on your phone.
I'm taking a video.
Okay, so it works. It has some values for how it will bounce. The code is boring. You can look it at home. Yodo, I heard you like decorators, so I put a decorator into a decorator so you can decorate where you decorate. I don't know how many people do that meme. It's old. This is sprites, which are bouncing, and they have differ, and they have interval. So I can apply several decorators to the things, and they work together. This is just to kill the idea that you can only apply one decorator to a symbol. You can apply any number of them, and they should work together fine. So I can take the base class and then do all decorators at once, and it works. And when you instantly instantiate the symbol, it will take all the options from the base class and all the subclasses and decorations. So it feels nice. It doesn't have to, once you have the decorated class, you don't have to put extra calls in there. It feels nice to work with. Now this is more interesting for us JS people, trajectories, because we have moving stuff. The thing that this decorator does, it duplicates the symbol several times, and then the GPU will filter one of them. So there's not one purple radar strip, there's two of them. One for each segment. And the GPU will filter one of them out, and the other it will interpolate the coordinate. It's all trickery and magic and mirrors. And it works. Yeah. It's nice. And a lot of people are asking for this kind of functionality. And I think that WebGL is kind of struggling with this, and I'm not, so that's nice. And it will work for any kind of point symbol. Okay, how it works, you take the line string geometry, a list of n values, and you get the class, and it works. Verify is one of these technical ones I use for debugging, because lines are hard. You say, oh, it's just a line, you draw a line, what the hell is this? No, you have to do triangles. And the triangles are hard, like real hard. And then we're used to this kind of line ends and the line joins, which are meter, bevel, and round. I don't like round because round things are hard. So I actually created a different kind of meter. So this one, I don't see if you see the red circle, but it's kind of, it's very into the corner. And this one is tangent to the circle with a radius of half the width of the line, which is a very fast way of drawing line joints which are looking nice, are not meter and not bevel. I find it useful, so it's hard to make things, and when I apply the verify decorator to a stroke symbol, I can see the triangles, and this works with any kind of symbol I want to debug how it looks with triangles. Scalar fields. If I ask you what a scalar field is, your answer depends on what your branch of academia is. For mathematicians, it is an injective function from the realm your realm into a real number. For us JS people, it's going to be a one-band raster. Okay? And since we are computer people, that one-band raster we're going to store it in memory, either in a texture in the GPU with a single component, not a band, a component. And if we're storing in the RAM, we're going to do two-dimensional array, right? Since we are doing things with WebGL and technology and stuff, we are limited to 32-bit floating point numbers. So when I talk about scalar fields, you might want to think this is a one-band raster with 32-bit floating point values inside that covers the screen or the map area. How Gleo normally works for rendering is it takes all the symbols of the same kind, it draws them in an acetate. How many of you went to university with one of these transparent sheet projector thingies? So do you know what an acetate is? Yes. Yes. I don't have to explain it, it's so nice. So I get a different acetate for all the fields, an acetate for all the strokes, an acetate for all the sprites, all the circles, all the etc, etc. Each of them has a specific WebGL shader. Then I squash them together with the platina. The platina is the glass surface of the projector. And then I put HTML on top. How it works with scalar fields is I got some symbols that will add value to the scalar field, to the raster data. Then, at a later stage, when everything is drawn to the scalar field, I turn that into an image, and then I squash it together. So the usual use case is the heatmap. We know these things. This data set is just population density. And, you know, it's a heatmap. It's smooth when you use it, which is real nice because I'm re-rendering one once per frame. I'm not re-rendering once per zoom level or anything. I can do this. So, you know, yes, I have done heatmaps. How do you do it? You explicitly create the acetate, you give the color ramp, and then you create the heat point, intensity, you add it to the map, and when you add it to the map, it will automatically find its way to the correct opacity, etc., etc. It's work. It's nice. It's an automatic kind of. I'm trying to make this easy to code, so you don't have to worry about all the details if possible. There's a couple of nice things called scalar fields. They will find a way. I can query the field, which I will show in the next slide. And just as a reminder, the main difference between rendering to a scalar field or to an RGBA texture is that when you render to RGBA texture, you're replacing color, and when you render to a scalar field, you're adding value. Okay, pixel queries. In order to show myself that there is a scalar field, I want to be able to query the pixel. So I can query both the color and the value of the field. By seeing the number, my brain understands that there is a field of numbers. How it works, you just put a pointer event, and it works. This is the same data set with a different blend equation. Instead of adding to the scalar field, you can choose to say, I'm going to choose the maximum of the current scalar field value and the value of your symbol. Same thing. It's useful for some use case to not add to the scalar field, but choose the maximum. You have to do some trickery to make it work, read it at home. I can decorate things, and I can take symbols which usually have a color and replace them with an intensity. So these circles, they don't have a color, they have a value. This is 100, this is 100, this is 59, and this intersection is 159. So it works as a scalar field. Right? What is this good one? You get the idea. What if I take a scalar field at a very, very low resolution and I draw things as 1 pixel? I get this pixelated thing, and then you realize this is an aggregation algorithm. Free. Like that. That's it. And of course it works and you can create the value. Now what if I show it a bit better? Instead of just draping this pixelated thing on top, I can just make it like small squares and create a texture, and yeah. This is a combin, and it's smooth and it works. Okay, and obviously, what if hexagons? I have hex bidding. I have real-time client-side hex bidding. And it works. It just works. And it's so smooth.
Sometimes.
I was this touch. What's happening with this touch?
Yeah, it's Windows.
Well, see it at home. You can choose between the quad bin and the hex bin. I get the intensified symbol. I create the hex bin with a cell size. I make the dot have an intensity and not a color. And I just add a lot of points to the map. It works. That's it. That's the actual code behind that demo. What if I put lots of data in this thing? This is 30 megabytes of AIS data. AIS is the thing that ships used to broadcast the positions. And of course, AIS data moves. And I can decorate things on top of things, so I can have a trajectory for all the ships. So I have like 10,000 ships all moving. And their size is adding to the value that the hex bin is reading. So I know kind of where are bigger ships and where not where are smaller ships. And it's so nice.
It's so nice.
It's really nice. And you can zoom in and you can see the tiny ships moving, and when they move to a different cell, the hexagon lights up. And it's just building things on top of things on top of things. If you see things blinking, it's because it's unfiltered AIS data. You know that half the work that we do is cleaning data. The other work is the actual work. So, well. But I'm really happy with this demo. Now, what if we animate the scalar field? Because I can do animations on symbols, and I can do animations on stuff. I can manipulate the rent loop. So I was talking with a French nuclear activist about nuclear graveyards. And this is readings she took from a region in France next to nuclear treatment plants. This is Geiger. This is a reading from a Geiger counter. So this is, maybe it's not showing too well on the projector. If you see on your own screen, it's really nice. Instead of rendering a color, I am rendering a probability of a pixel lighting up at any given point in time. So the places with a higher Geiger counter reading will most probably blink as white, and the places with a lower reading will have a lower probability of blinking. Since it's a scalar field, I don't have to render a heatmap. I can do different things than that. And one of them is going to be weird. I can take points data with a numeric value. I can build a delta mesh of that data to make a field of that number. And instead of showing that data as color or blinking pixels, I can apply a modification to a previous image, which looks like this. This was last week's weather forecast for Spain. This is the temperature forecast. We were hitting something like 44 degrees. I guess you know which area. Because the people that have seen this example, they start sweating when they see it. This, my friends, is a heat map. And that's the last example. My library is in there, and please use it.